Another common application of hydrostatic force balances is in the field of buoyancy. Buoyancy is probably something that you've all remember learning about a long time ago, and the idea is that we're going to be interested in thinking about forces on an object that might be immersed in a fluid. And so if I take an object like this and I put it in a fluid, then the fluid we're going to indicate as having a density which we'll be very careful here to just call rho f. And the object itself might have a density rho object. And so it would have a body force acting on it like this, which we could either express as mass times gravity, or we might express it in terms of the density of the object and the volume of it as well. An Archimedes principle, as you will remember, is that any body that happens to be immersed in a fluid experiences a buoyant force directed, we'll say upwards. But by that I mean in the opposite to the direction of gravity. And the buoyant force, which is proportional to the volume of fluid displaced. And so people will often talk about displacement, or the amount of fluid that I push out of the way. We can derive this result very easily using Gauss's theorem, which we talked about last time, by recognizing that our hydrostatic force balance looks like this. And what we're interested in is we're really interested in finding the integration of the pressure force acting on our material that's acting over the surface. And we remember that pressure forces are acting inwards, so at every little material element here I have an outward-facing normal N, and I have an inward acting pressure P, which is a function of position and maybe also a function of position and time, although we're going to think about a system in equilibrium, so we don't have to think about this. But we know that from hydrostatics that the pressure is going to be unevenly distributed, and the further I go down, the larger the pressure is going to get. And so we need to find this integral over the area, and we can use Gauss's theorem to convert this into the gradient of the pressure. It's a scalar, so our divergence operation becomes the gradient, and this is going to be integrated over the volume that we're going to integrate over, which is the volume of our object. And this thing is indeed nothing but the buoyant force that we're interested in, and we'll call it FB. And so I need a minus sign in here to keep our signs correct. And I know an expression for this from my expression for hydrostatics right here. And so I can easily express it in terms of here as minus the integral of rho g dv integrated over the volume. And in this case, if we're dealing with an incompressible material and gravity is constant, everything that's inside here can come outside the integral. And so our buoyant force is indeed directed opposite to gravity. And it's integrated of 1 dv, so it is indeed just integrated over the volume of the object. And this is our expression for the buoyant force. And this is where we have to be a little bit careful about which density it is that's in here. So if we think about what we've done here, we certainly did an integration over the surface of this. We converted it into a volume integral, but what we're integrating over is the distributed pressure arising from the fluid that's all the way around my object. And so I'll try and indicate the arrows as getting bigger and bigger when I'm down here. And we are really thinking about the pressure that's in the fluid surrounding here. So when we did this for a hydrostatic balance of a fluid. So this was the density of our fluid. This is the density of our fluid. And this is the density of our fluid. So indeed, the force is proportional to the volume, but it's the volume of the object, and that's displaced fluid. And so the force scale actually depends on the density of the fluid multiplied by the volume of the object. And that's a really important thing to remember. That's why when you look at ships and you see the size of a ship, they will frequently say it has a displacement of so many thousands of tons, because indeed what they've measured is they've measured the displacement of water. Typically as they put the boat into water. So this is completely equivalent to having done this distribution, and so bear in mind that when we write down the idea of a buoyant force, and we've just worked out what the buoyant force is, the buoyant force that we've just worked out is acting in this direction. It's acting in the opposite direction to the body force. F due to gravity. But don't double count things. It's very common when we get to problems later on to say, oh, I've got to think about the distribution of forces and a buoyant force, but the two things are exactly the same. So it's really the integration of this uneven pressure field around here that is given rise to the buoyant force, and we've done that integration. So don't double count things as you go on. The final thing that we might point out is for floating objects. So if we're dealing with a floating object, like let's say a ship, then we have to bear in mind that we really have to do the distribution, and we have to be careful to recognize that there may be two volumes, which we can call V1 and V2, because there's different densities, let's say, of fluid and air around there. And so the buoyant force that we might see here would be equal to the density of air times gravity times V1, and that will be pointing upwards. And then there would be a second contribution from the density of the fluid times gravity times V2. That would be also a minus sign. So they're both acting opposite to gravity, where gravity is acting in this direction. And typically, of course, the density of air is much smaller than the density of the fluid that we're interested in. So this term is frequently neglected, and we really only have to worry about this term. And so indeed, this is what people would refer to as the displacement of a floating object. But it's worth bearing in mind, if you stepped on a scale this morning that, and you weighed yourself and you measured how much you weigh, you might well have realized that now that you've forgotten to subtract the mass of air that you've displaced. So there's actually a slight buoyant force acting on me from the air that I've displaced in this room. However, the contribution is very small.